This video, we're going to take a little bit of time to discuss the benefit of using arbitrary constants when you're solving certain separable differential equations. So in this video, we're going to talk about solving this differential equation, solving this differential equation. They're very similar to one another. The only difference would be the y value of the initial condition. And we'll solve them at first without using an arbitrary constant. But then we'll talk about the benefit of using this arbitrary constant and why it's something that you'll probably frequently be doing while you're solving separable differential equations in your calculus or differential equations course. So this first differential equation, I'm going to separate my variables, so I'm going to divide both sides of the equation by y. I'm going to multiply the dt across. I'm just going to leave the 5 alone. I'm going to integrate both sides. When I do the integral on the left, I get natural log of the absolute value of y. Technically, I should put a constant on this left side of the equation, but I'm accounting for the constant on the right side of the equation. And what I want to do is I want to solve this equation for y. So when I just combine two constants into a new constant, I just get that new constant on the right side of the equation. So that's also something you've probably discussed doing in your differential equations work. Now I want to isolate y here. So what I'm going to do is I'm going to exponentiate on both sides. Now when I do that, one of the things I see my students have the tendency to do is just kind of drop these absolute values. I want to make sure you realize why I cannot do that after taking both sides and exponentiating. E to a power is only ever going to be a positive answer. If that power is positive, you get a positive answer. If that power is negative, you get a positive answer. E to a power is positive 100% of the time. Because the right side of my equation is positive 100% of the time, I must maintain the absolute values on the left side of the equation so that it's also only ever positive. Now here's what this amounts to. Y is going to be equal to e to the 5t plus c if y is greater than 0, but if y is negative, y is going to be equal to the opposite of e to the 5t plus c. So if we don't use an arbitrary constant, we're going to have to judge on a case-by-case basis whether or not we need a negative sign in front of our base e or a positive sign in front of our base e. Now if I use this initial condition, I put 3 in place of my y value, I put 1 in place of my t value. Y is positive, right? 3 is positive, so since y is positive, I maintain the positive sign in front of the base e. I do a little bit of algebra to solve for c. Here would be my specific solution. So we have two forms of the general solution dependent on the sign of y. And then here's the specific solution that uses this initial condition. And when I click ahead, you're going to see all this work at the top of the screen is going to be applied again. And this should make sense why. The only thing that changes in the next version of the problem is the initial condition I'm going to be using. So I've got all the same work up here, but now when I plug in my initial condition, I put a negative in place of y, and the only way that I can have the two sides of this equation equal to one another, if a negative's going in for y, I'm going to need to maintain use of the negative in front of the base e. So I can then divide both sides by that negative, and then the sequence is really the same from there. So the second solution that we've developed for this, the new solution we've developed for this slightly modified differential equation is the same as the first, just with the negative out here. What we want to talk about on the next screen is how we can avoid having to break this into cases and having to decide, okay, which case am I in for the current problem? So here's just the differential equation without any initial condition listed. I'm going to separate my variables, integrate both sides. I still get to this same line right here, right? We've seen this in each of the first two examples we've done within this video. I'm then going to start to manipulate this right side of the equation. You add in an exponent when you're multiplying like bases, right? Think about x to the 5th times x to the 3rd. That's really equal to x to the 8th. When you multiply like bases, you add the exponents. Well, what we have right here is we have addition in that exponent. I can go the other direction with this property. I can take the addition in the exponent and re-express it as multiplication of like bases. So I'm doing that with e to the 5t times e to the c. Now what you'll hopefully realize about e to the c, e is approximately 2.7. C is a constant. If I take a number and I raise it to another number, what I've highlighted right here is some other number. Now here's the thing that causes some confusion, and this is weird. Hopefully this is going to make decent sense after we hash it all out. E to the c is only ever positive. But if I re-represent e to the c, notice I'm not saying e to the c is equal to a right here. I'm saying e to the c is being re-represented by an arbitrary constant a. If I allow this arbitrary constant a to take on negative values, I don't have to worry about the two different cases that we were talking about on the prior screen in order to get rid of the absolute values. The transition of addition in the exponent to multiplication of like bases, recognizing that one of the pieces of this product is a constant, re-representing it with an arbitrary constant, and allowing that arbitrary constant to become negative when it needs to be, allows you to bypass having to do what we talked about on those first few screens. So I know that's a little bit of a weird thing to say. Okay, I'm replacing this with something, but it's not necessarily equal to it. The benefit to replacing it with the arbitrary constant is that the arbitrary constant can take on the sign that we need, and we get to bypass any of that case-by-case analysis like we did in those first two examples.